An AC generator converts mechanical energy into electrical energy. In its simplest form, an AC generator consists of a rectangular coil mounted on a rotor shaft. The coil is also referred to as the armature. The coil is placed in a uniform magnetic field. The axis of the coil is normal to the direction of the magnetic field. The coil, or the armature, is mechanically rotated in the uniform magnetic field by some external means. Let the number of turns in the coil be N. The ends of the coil are connected to an external circuit by means of slip rings and brushes. The coil rotates, inducing an EMF and a current in itself. The current induced in the coil is fed into external circuits through the slip rings that act as terminals to the generator. Let us now find the expression for the EMF generated by an AC generator. Consider the area vector A. For the coil, the area vector is normal to the plane of the coil. Initially, let the area vector lie in the direction of the magnetic field. This implies that plane of the coil is normal to the direction of the magnetic field. Let theta be the angle between the area vector A and the magnetic field B at a given instant of time t. When the coil is rotated at a constant angular velocity omega, the value of theta at the instant of time t is given by the equation theta is equal to omega multiplied by time t. Let this be equation 1. The effective area of the coil which is linked with the magnetic field is A cos theta. From equation 1, it is clear that the effective area of the coil is a time-dependent function. In other words, the rotation of the coil causes the magnetic flux through it to change, thereby inducing an EMF in the coil. The flux induced in the coil at any instant of time is given by the equation phi B is equal to BA cos theta. Let this be equation 2. On substituting equation 1 in equation 2 and simplifying, we get the equation phi B is equal to BA cos omega t. Let this be equation 3. From Faraday's law, the induced EMF for a coil of N turns rotating in a magnetic field is given by E is equal to minus Nd phi B by dt. The negative sign is in accordance with Lenz's law. On substituting the value of phi B from equation 3 and simplifying, we get E is equal to minus Nd by dt of BA cos omega t. The strength of the magnetic field B and the area of the coil A are constants. The equation now transforms to E is equal to minus NBAd by dt of cos omega t. From differential calculus, we have d by dt of cos omega t is equal to minus omega sin omega t. Hence, the instantaneous value of the EMF E is equal to NBA omega sin omega t. Let this be equation 4. Note that NBA omega is the maximum value of the EMF that occurs when the value of sin omega t is plus or minus 1. That is, when theta is 90 degrees, or 270 degrees. This is because the change of flux is the maximum at these two angles of the coil. As the value of sine function varies from +1 to -1, the sign or polarity of the EMF changes with time. Accordingly, the direction of the induced current changes periodically. For this reason, this current is called an alternating current. Let us denote the maximum EMF NBA omega as E0. Then, the instantaneous EMF E is equal to E0 sine omega t. Let this be equation 5. We know that omega is equal to 2 pi nu, where nu is the frequency of revolution of the generator's coil. Substituting the value of omega in equation 5, we get E is equal to E0 sine 2 pi nu t. Let this be equation 6. Thus, equation 6 gives the expression for the instantaneous value of the EMF.